Let's start our Congress. I introduce myself. My name is Talgat Nebayev. I'm an invited professor in Eurasian National University. It is great honor for me to open the International Second Turkic World Congress on Science and Engineering. On June of 2019, Turkey hosted the first International Congress of Turkic World of Science and Engineering, organized by Niğde Ömer Halis Demir University in cooperation with Eurasian National University. About 250 scientists from 10 countries attended that Congress. Unfortunately, now we cannot hold the conference face-to-face for all known reasons, and this Congress is being held online. Today, at plenary session attend Rector of Niğde Ömer Halis Demir University, Professor Muhsin Kar, Vice Rector of the Science and Innovation of Eurasian National University, Professor Gulnar Mirzadinova, Vice Rector for International Cooperation of Eurasian National University, Professor Agbota Jaldazbekova. Also, in this Congress attend representative of Embassy of Turkey in Kazakhstan, Ambassador of Kazakhstan in Ankara, Abzal Saparbekulu, and Ambassador of Turkey in Republic of Kazakhstan, Ufuk Ekiji. Now I'm very pleased to invite Vice Rector of Science and Innovation of Eurasian National University, Professor Gulnar Mirzadinova, to give a welcome speech for Congress participants.
Құрметті конгресс қатысушылар, қадірлі қонақтар. Меня слышно?
Да, слышно.
Уважаемые участники и гости Конгресса. Dear participants and guests of the Congress, let me say welcome to Global Turkic World International Congress. Allow me at the outset to congratulate you with the beginning of International Turkic World Congress in Science and Engineering. I am thankful to all of you who have postponed important work on this tough time and how are participating in the important forest scientific forum. Congress program considers the most topical global problems in engineering sciences and discusses approaches to resolve these issues. The Republic of Kazakhstan in the world era proclaimed itself as a developer of advanced science-intensive technologies. It should be noted that Gumilev Eurasian National University professors make a major contribution to improve these technologies. Our university is the only higher education institution in Central Asia which is included in QS top 50 under 50. Being one of the most leading national universities in Kazakhstan, Eurasian National University defines scientific activity is one of the top priority direction on the work. Our scientists' investigation take pride of place in the world. University position both in Central Asia and in global university. For example, according to QS World University ranking, our university is 350th place out of the 1,000 in other world union. Is in the top 400 universities. It is considered as a good index for young university, which is to be 25 in the upcoming year 2021. It is my pleasure to highlight that our university is top 1,000 according to Times Higher Education World University ranking. It has been quite expected as one of the most powerful schools on technical directions and concentrated is our university. It should be noted that Republic of Kazakhstan pays considerable attention to science and technology development. Currently, in state is increasing financing of scientific research by 2025. The state is planning to expand the volume of the finance up to 1% out of GDP. According to Ministry of National Economics prediction, GDP in Kazakhstan will be worth 69.7 trillion tenge to 155 billion US dollar by the end of 2025. There are examples when innovation technology developed in Kazakhstan scientists in the short time are commercialization and becoming successful product in economics, healthcare, and applied manufacture. Today, in spite of complicated political and economic situation in the world, International Turkic World Congress unified all nations of Turkic world to resolve sciences and technology problems. I hope that having exchanged knowledge and experience will be make major contribution in resolving global fundamental issues. I wish health and success to all participants along with fruitful work in Congress. Thank you for attention.
We cannot hear. Excuse me. We cannot hear the.
Талгат Муратович, вас не слышно.
Sorry, I'm muted. Well, thank you, dear Professor Mezadinova, for your welcome speech. And now I invite Rector of Niğde Ömer Halis Demir University, Professor Muhsin Kar, for greeting the Congress participants. We don't hear you. No sound.
Microphone.
Yes. Dear ambassadors, dear rector, and distinguished guests and participants, respected colleagues and students. On behalf of my university's academic team and administrative staff, I would like to welcome and greet all of you with health, peace, and happiness, and thank all the participants who have come from various parts of the world to attend this International Turkic World Congress on Science and Engineering. 2 years ago, we have signed an agreement with Gumulyo Eurasian National University and jointly initiated a number of scientific activities, which include establishing a research center for Kazakh culture and education, exchanging students and staff, conducting projects, and initiating both an international conference and a scientific journal on science and technology. In addition to this conference, we already started to exchange students and academic staff between our universities. Therefore, furthermore, as an integral part of this conference, we have jointly started to establish an international journal, namely Eurasian Journal of Science, Engineering and Technology. I am therefore very pleased to see the achievements and smooth developments of the fruitful results of this collaboration. As a Niğde Ömer Halis Demir University, we want to expand and deepen our relations with Eurasian National University by all means. We believe that closer collaboration will be beneficial for both our universities and the welfare of our societies. Special attention to our universities and countries is therefore needed to express the role of initiation of these scientific events. Dear participants, we also contemplate that this sort of scientific meeting is a platform for the academics from all over the world. We believe that science is a common knowledge for the humanity, and we all can contribute and get benefit from it. We all know the importance of developments in science and technology in the welfare of the societies. Investing in education, in particular science and technology, is very vital for the future of every country. We, as the Turkic and Islamic world, had made an important contribution to the scientific advances in the past. It is becoming clear that during the dark ages of the medieval Europe, incredible scientific advances were made in the Muslim world. Geniuses in Otrar, Farab, Samarkand, Baghdad, Cairo, Damascus, Cordoba, took on the scholarly works of ancient Egypt, Mesopotamia, Persia, Greece, India, and China, developing what the world called modern science nowadays. New disciplines emerged: algebra, trigonometry, and chemistry, as well as major advances in medicine, astronomy, engineering, and agriculture. And however, for a long time, we have been following the scientific advances developed mainly in the Western rather than leading. There might be the practical and conceptual consequences of science and technology pressing for the Muslim societies. In order to lead the scientific innovation, we have to revise our approach to science and technology and treat the knowledge produced in the world as a public good. We need to make a balance between science and Islam and widen our understanding to conceptualize the scientific innovation within our faith, wisdom, and understanding of the universe. Dear participants, one of our aims should be to provide new platform like this conference for the scholars from all around the world, share knowledge and wisdom, improve academic capacity in our universities, contribute to the scientific advances once again, and increase the welfare of our societies. I am confident that all the participants, experts in the conference, will not only share with us their precious knowledge, wisdom, and experience in their respective fields, but also cast their valuable perspective and insights into the understanding of various aspects and implications of the conference main theme. Moreover, they will offer fresh projections for prospective studies and researches to be conducted in the future. I would like to welcome and thank both of them for accepting our invitation and coming to the conference in these difficult days for the humanity because of pandemic. We had to organize this scientific event online. We will have an opportunity to listen to these distinguished scholars from 15 countries. There will be 172 presentations in the conference. In concluding, I wish to reiterate my heartfelt gratitude to all the guests and participants, national and international alike, for being with us in this international scientific convention. I would like to thank Rector Professor Dr. Yerlan Sidikov of Eurasian National University, who host this meeting and make it possible. My special appreciation goes to the chairman, Professor Dr. Gulnara Merzadinova and Professor Dr. Murat Barut, and members of the organizing committee of the conference, who have all been working for nearly a year, day and night, behind the screen to make this event a huge success. Once again, I would like to thank you for participating in the conference, and I hope to meet you face-to-face in the next year meeting and wish you all a successful conference.
Dear Professor, thank you very much for your warm greeting. And now, representative of Embassy of Turkey in Kazakhstan, Ambassador of Kazakhstan in Ankara, Abzal Saparbekuli, will give a welcoming speech. Please.
Құрметті бүгінгі конгресске қатысушылар, барлықтарыңызға Түркиядан, Анадолы елінен ең ыстық сәлемді жеткіземін. Менің даусым естіліп тұр деп ойлаймын. Естіліп тұр ғой, да? Sayın Rektörüm, günaydın. Benim sesim geliyor mu size?
Günaydın Sayın Büyükelçim, geliyor sesiniz.
Tamamdır. Buradan herkese günaydın diyorum. En kalbi duygularımla muhabbetle, sevgiyle selamlıyorum. Bu zor günlerde herkese sağlıkta kalmasını diliyorum. Барлық қатысушыларға ең ыстық сәлемімді жеткізе отырып, барлықтарыңызға осы қазіргі қиын сәтте барлықтарыңызға денсаулық тілеймін. Менің видеом көрініп тұр ғой деймін да сіздерге. Videom da geliyor değil mi Sayın Rektörüm? Görüntü var mı?
Görüntü var Büyükelçim.
Tamam.
Görüntünü de alıyoruz, sesini de alıyoruz.
Evet. Dear my rectors, dear vice rectors, respective science and students, dear participants of the conference, I would like to welcome all of you and wish the most successful Congress work. The Turkic world is a topic that is becoming increasingly important in international relations. I would like to say some words on the vision of Kazakhstan in this regard. Since the independence of Kazakhstan, the first president of our country, Nursultan Nazarbayev, pursued active foreign policy in order to establish close cooperation with the Turkic countries. At the initiative of His Excellency Nazarbayev, the Turkic Council was established in 2009 in Istanbul, and the International Turkic Academy was also opened in 2010 in Nur-Sultan. You know very well there is also a union of Turkic universities, of which Eurasian University is an active member. This active policy of Kazakhstan towards the Turkic world continues during the President Kasım-Jomart Tokayev as well. On April 10, 2020, at the summit of the Turkic Council, the leaders of the member states have agreed to increase cooperation in scientific research and medicine among the Turkic countries in the light of the pandemic. Dear participants, it's very meaningful that the Congress is held in the year when UNESCO celebrates the 1115th anniversary of Al-Farabi, our great ancestors. In this context, I would like to underline that it's not coincidence that all Al-Farabi and the majority of scholars of the Islamic Renaissance period were originally from Central Asia region. Just it was the case during the golden age of Islamic civilization, I believe that now the science of the Turkic world can make their contributions to the development of science and technology of humankind. For that purpose, close cooperation among the scientists of the Turkic world, more broadly of the Islamic world, is necessary. In this direction, with the initiative of Kazakhstan, the first Science and Technology Summit of the Organization of Islamic Cooperation was held in Nur-Sultan in September 2017. As the result of the summit, the Astana Declaration, which emphasized the need to increase the investment of Islamic world countries in the field of science and envisage increasing cooperation in the field of technology and innovation, was accepted. To sum up, for the Turkic and Islamic world to make a breakthrough in science and technology, it is necessary to establish cooperation among scientists. It's especially gratifying that Kazakhstan and Turkish scientists and universities are developing joint projects. I hope that this cooperation will yield important results and that our young scientists will follow in the footsteps of Aziz Sancar, who is the only Nobel Prize winner of the Turkic world for now in the field of science. In this respect, I hope that International Turkic Congress on Science and Engineering will be fruitful. I would like to highly appreciate the organizers of this important event and wish success to all scientists who present their research in the Congress. Thank you very much.
Okay, thank you very much for your greeting. And now we should, after 8 minutes, we should start the scientific part of our Congress. And now I think we should start on time, yes? exactly, because maybe some other people will connect a little bit later.
Yeah, we can make a break.
Okay, let's wait for. Okay, official part is finished. Let's wait for 7 minutes and start the scientific part.
New.
Okay. Since we have some break, we have a few minutes, I will explain the technical details of this plenary session. Okay. Each speaker will have 30 minutes for talk. Usually, I offer to spend 25 minutes, for example, for talk, and 5 minutes will be for discussions and questions. And please, I apply to all the speakers, please check the time. Okay, okay, and since okay, first speaker, I see he is ready, and let me spend 1 minute to introduce him. First speaker will be Professor Dr. Mohsen Sheikhoul-Islami. He works at the Babul Noshirvani University of Technology Department of Mechanical Engineers in Iran. He is head of renewable energy systems and nanofluid applications in Heat Transfer Laboratory at Babul Noshirvani University of Technology. His research interests are nanofluids, CFD simulation, mesoscopic modeling, nanoscience, and electrohydrodynamics and heat exchangers. He is one of the most cited researchers in the world. His H index is 114. This is unbelievably high value. And okay, it's time. And please, Professor Sheikhoul-Islami, please, you can start your talk.
Hello, everyone. Can you see my PowerPoint?
Yes.
Okay.
Please just magnify it.
What?
Please make full screen of your.
Yes, I use full screen if you check. Hello, everyone. Thank you for having me. Thank you very much for your kind words. I'm so much honored to be among a wonderful research community at your university. I shall express my most sincere gratitude toward the administrative people who have organized this conference just flawlessly. Before I start, I want to introduce myself. My name is Mohsen Sheikhoul-Islami. I'm a faculty member of mechanical engineering at Babul Nushirvani University of Technology and the head of renewable energy systems and nanofluid application in heat transfer laboratory. I'm going to be speaking to you today about the nanofluid application for renewable energy, especially solar energies. To begin, categorizing renewable energy is important. This slide summarizes the contents of my presentation. Source of energy, solar collectors, nanofluid, finally introducing my research laboratory are main contents of my presentation. As you know, there are generally two sources of energy. Those sources of energy which have been produced in nature over a very, very long time and cannot be quickly replaced when exhausted are called non-renewable source of energy. Such sources stores with zero rate of replenishment relative to its depletion by human beings. Most non-renewable energy sources are converts to usable energy by thermal or nuclear reactions. However, non-renewable energy are not viable, and the demand of using renewable energies has extremely increased. Opposite to non-renewable energy sources, those sources of energy which are being produced continuously in nature and will never be exhausted, called renewable source of energy. Renewable source of the energy which are essentially inexhaustible energy in a human time. Human time scale consists of solar power plant, wind energy,
Professor
bioenergy, and etc.
We cannot see your PowerPoint. You are not changing the pages. Maybe you are not sharing your screen, computer screen.
I share my PowerPoint. We checked before.
Just first page we are able to see. Please cancel your screen sharing and then re-share your presentation.
Just a moment.
Please don't make screen full.
Sorry for breaking
It's
you.
my request.
Is it okay now?
Okay. Please change your slide when you are talking. Now we are able to see renewable energy sources
No,
page.
I changed.
So
I changed, but I think you cannot see. Did you say? Do you see my new slide?
Yeah.
Can you see the changes?
We only see renewable energy sources page.
Oh, so you cannot see. Let me try another way.
Please make it full screen.
Okay.
You need to share your screen directly, not the Microsoft PowerPoint page. Directly share your screen. And then
no, I do that.
Yes, now you did. Yeah, that's great now. Okay, please go ahead. Yeah.
Okay. As I said, the renewable source of energy can be categorized in wind energy, solar energy, and etc. And we focus on solar energy. Solar energy is a most readily available source of energy. It does not belong to anybody, so it's free. It is the most important of non-conventional source of energy because it is not non-pollutant and therefore helps diminishing the greenhouse effects. One of the main solar energy, we should say about how it works. We can categorize it in three groups. Solar power plants in which steams produced to turn turbine. Solar heating, which is consists of active and passive techniques, and finally photovoltaic cells. Of the main advantages of renewable energy systems, we can say renewable and free, high energy yield, low operating cost, the clean source of energy. Also, it has some disadvantages such as its low energy density. We particularly focus on solar energy for my country, which has a high potential to gain from this type of energy. Iranian government have been installed number of solar panels on rooftops around the country, everywhere from schools to government building. Over 1,000 new locations at especially at rural areas. Inactive solar heating, especially design collectors, absorb solar energy and pump distributes energy to parts of building. And passive solar heating, and passive solar heating captures the sunlight directly, which is structured and converted to low temperature heat for space heating. Of the main advantages of solar heating, we can mention to save money, eliminating fossil fuels, less pollution, and environmental dangers, environmental damages, and being expensive in initial cost is its main disadvantages. We are blessed energy in abundance at no cost. The solar radiation incident on the surface of the Earth can be conveniently utilized for benefit of human society. One of the popular devices that harness the solar energy is solar water heater, which consists of a collector to collect solar energy, and then insulated storage tank to store hot water. The water passing through the riser and gets heated up, and collector raise the temperature to 80 degrees Celsius in a good sunny day. Broadly, the solar heater has two categories: the closed systems and the open system, the left and the right picture. In the first one, the heat exchanger are insulated to protect the systems from the hot water obtaining the freezing temperature and in cold region. In other part, either thermosiphon or forced circulation systems. The water in the systems is open, and the water in the systems is open to atmosphere at one or other points. Open systems has various advantages such as its good efficiency. In addition, it has some disadvantages such as these systems can overheat, and repair is expensive. In current slide, we present some advantages and disadvantages of closed loop systems. The main Advantages are will not freeze, will not overheat the pipe drain when system is not working. Good for cooler climate where freezing is likely. And main disadvantages are maybe difficult to fit, must purchase antifreeze, and must implement heat exchanger. The choice of system depend on the dependent heat requirements, weather condition, heat transfer fluid quality, space availability, annual solar radiation, etc. Such systems are economical, pollution-free, and easy for operation in warm countries like Iran, Turkey, and something like that. As I previously expressed, the solar radiation can be absorbed by a flat plate solar collector, which is consists of insulated outer metallic box covered with a glass sheet. The absorber absorbs the solar radiation and transfers the heat to the water. In this slide, we present some features of solar water heater, such as it is insulated on rooftops and only soft water and potable water can be used. Nanofluid can be defined as a fluid containing nano-sized particles. The nanoparticles are generally made from metal or carbon nanotube. The base fluid consists of water or oil. The nanofluid have special properties that create them helpful in several applications in phenomena involving heat transfer. The thermal conductivity data for various nanoparticles is listed in this slide. Adding nanoparticles into base fluid can change the thermophysical properties. It should mention that there are two methods to produce nanofluid: two-steps method and one-steps method. To answer the question why there is a significant interest in using nanofluids, I must note that nanofluid causes thermal conductivity to increase thermal conductivity, and advantages such as reduction in heated loss, radiation heated loss. When nanofluid is used, radiative and convective loss reduces due to increasing in heat transfer between the absorber plate and nanofluid. Augmenting techniques can be classified as passive and active methods. Passive techniques requires no direct application of external power. Using a turbulator is a passive technique for heat transfer enhancement. You can see various turbulators in this slide, which exist in our publications. To better illustrate the point, I will present example. An example in this example, heat transfer within a collector with insertion of twisted tape inside the pipe has been analyzed. Aluminum nanofluid selected as working fluid, and application. And its application is due to its lower price and greater usage in solar energy systems. We used ANSYS Fluent software for simulation. The details of simulation can be shown in this slide. When nanoparticle is dispersed, the increment of thermal properties has been occurred. In this slide, you can see the impact of adding various type of nanoparticles on second law performance. This parameter increases with dispersing nanoparticles. The maximum and minimum values of second law performance are obtained for multiple carbon nanotube and titanium and titanium oxide, respectively. The difference in various type of nanoparticle is more pronounced in greater Reynolds number. The effect of geometrical parameters on nanofluids behavior and second law performance are shown in this slide. As you can see, increase of diameter and the number of revolution lead to increased performance of the system. Secondary flow becomes stronger with rise of revolution and diameter ratio. So Nusselt number increasing is an increasing function of both parameters. Selecting greater values of diameter and revolution leads to greater thermal performance. Greater turbulence intensity is found in case with greater revolution, which the reason why Nusselt number has direct relationship with number of revolution. And then in the next step, we utilize multi-channel to this step. Solar heat flux affect the upper side of the pipe and the absorber. According to this slide, the nanofluid can move easier with rise of number of channel and a stronger secondary flow generates. If better mixing of nanofluid occurs, a stronger vortex helps the convective flow and Nusselt enhances. So second law performance enhances with rise of 4 parameters. As I said earlier in introducing myself, I am a principal investigator of Renewable Energy Systems Laboratory. We conduct several interesting publications in field of nanofluid, which were published in reputable journals. Due to our efforts, our university ranked as first of Iran, and according to Times ranking. I'm very excited. I'm very excited at the prospect of collaboration with you, particularly in simulation-based research. My team and I are always ready to extend our cooperation in the international level. Here is my phone number and email address. Thank you very much. I'm really pleased to be here. I would like to thank the organizers of this conference and university staffs and faculties. I hope my talk was humorous enough. After my talk, I will be around to answer any question relevant to my realm of expertise.
Thank you very much for a very nice talk. We have about 10 minutes for questions and discussions. Any questions?
Thank you very much for your presentation. Professor Monsi Michel calls Lamy and participate in these great events. Very interesting issues. I think it's very important nowadays. One question, Professor. What kind of these solar panels do you can be used in our conditions? Because you know our weather, it's very cold and we not enough have solar. That's why it's impossible to implement your technologies in our conditions. Thank you.
Thank you very much for your kind words. Actually, the solar systems, for example, for flat plate collectors or linear furnace systems and other kind of systems can be places in which solar radiation rate is good. And for the main concept of my presentation is this fact. And for the other parts, I think it is not beneficial to use these such systems according to its economic limitations and based on what I'm said, the price of initial setup of such systems is high, so it is not recommended to use in cold regions actually, and that's why we use in places such as Iran. So because its direct radiation is high in over the part of my country. About the cold regions, these systems cannot be used, but I should search more about the such regions to find a better way for such regions.
Thank you very much for your answer. I understand you. And if you understand correctly, this is solar. You can be used just only part of it is the weather. It's very hot. I think the efficiency to use these technologies is very effective. I think.
Okay, thank you. Any more questions? May I ask you a question? Your result of your research is commercialized, or do you collaborate with some industries or energy companies to realize your ideas in practice?
We collaborate with some industry company in Iran, and what I am present in this presentation is our simulations results, and we have other results based on experimental procedure, which are the result of collaboration with industry and as you said, we can use the benefit of these systems in industrial companies, and we have planned to this.
No, okay, thank you. More questions?
Yes, I would like to ask a question. I am Dr. Hafiz from KFUPM. Okay, so can I go ahead?
Do you have a question?
Yeah, I do have a question.
Please ask.
Yeah, thank you. Dr. Mohsin, thank you for the nice presentation. I would like to know that are you considering phase change as well for your solar collectors?
Hello, Dr. Hafiz. Excuse me. Can you repeat again your question? Which parameter?
I'm just curious to know that you are considering phase change, or you are simply doing your simulations for single fluid.
In this presentation, I focus on just papers on which are published on solar color without any phase change. But as you better know, it can be mixed with phase change material systems, and the combined systems can be used. Yes.
Yeah,
But in this slide, there is in my presentation there is no any results about these applications.
Okay, so thank you very much.
Thank you very much.
Okay, thank you for a very nice talk, very interesting discussion. And let me introduce next speaker. Next speaker is researcher who asked the last question for previous one. His name is Professor Ali Hafiz Mohammed. He currently working as an associate professor of mechanical engineering at King Fahd University of Petroleum and Minerals in Saudi Arabia. His scientific interest is thermal science and heat transfer, solar energy. And title of his talk is Augmentation of condensation heat transfer on enhanced tubes. Please have 30 minutes.
Thank you very much for giving me a chance to present my work. So before I could start, I just shared my slides. So I would like to get a confirmation if you guys can see my slides.
Yes, but I think you should make full screen for PowerPoint.
Yeah. Okay. So is that fine now?
Yes, yes, but this is important because when we will change slides, we will not see this change. As previous speaker has the same this problem, and this is better. Yes, yes, good.
Okay.
Yes.
Okay, that's great. Okay. So thank you very much once again for inviting me to present some of my work in your conference, which is related to the stuff regarding thermal sciences and heat transfer. So as an introduction, I am Dr. Hafiz. I'm working as an associate professor in mechanical engineering department of King Fahd University of Petroleum and Minerals. Mainly my work is in the area of heat transfer. So condensation heat transfer, you know, this is one of the important area when we talk about, you know, power generation, and it has a lot of applications there. So my today's talk, this will be specifically about condensation heat transfer on enhanced tubes. So we are going to consider during this talk the condensation on the external tubes only, because in power stations generally where we have steam, after once the steam is coming through the turbine, it goes to the surface condensers where we have this condensation process. So if we can make this process efficient, then it is actually going to impact on the performance of the whole system. So that is why this area is really, really important, and people are working on this area for a number of decades now. Okay, so we will try to look into the progress that how this work was started and where we are now in terms of enhanced tubes. So I'll be just focusing on the enhanced tubes. So what do you mean by enhanced tubes, which are geometrically enhanced tubes? So as an overview here for the presentation, you can see that I have presented here two different tubes. Like in the first figure, you can see this is simply known as integral fin tubes. So this has simple fins around the tubes. And the one which I would like to compare the results with, these are the pin fin tubes. So pin fin tubes are mainly, you know, these are three-dimensional tubes. So we would see that these tubes would be having some of the advantages when we compare them the integral fin tubes. Okay, So two-dimensional integral fin tubes, these are the basics tubes, and the mechanism of condensation of heat transfer on these integral fin tubes are relatively well understood, and we have some good empirical correlations that can be used to characterize heat transfer coefficient and to optimize geometries. But nowadays, a lot of attention is going to be paid to pin-fin tubes. So we have relatively good data on such kind of tubes, but we are still, working in terms of modeling, and there is still a lot of room so that we can develop some good models. But for sure, one thing that has been realized so far, that these pin-fin tubes are better when we compare them to the integral fin tubes. Okay. So in this presentation, I'll be reviewing earlier work on two-dimensional integral fin tubes, and then we will show the ideas that how semi-empirical models were developed for such tubes, and then this can be extended for the pin-fin tubes, which are actually three-dimensional tubes. Okay, so here you see that this is a simple diagram or simple picture of integral fin tubes during condensation. So once we have condensation on such kind of tubes, after condensing, the steam will be, liquefy, and we can have some of the liquid, staying on the lower part of the tube. Okay, so this liquid, which is generally known as retention as well, it is not considered good for heat transfer, because once this would be there, then it could be presenting like insulation to the tube. So the heat transfer to the tube from that part, this will be really decreased. So this is one of the reasons that when such kind of tubes like integral fin tubes were introduced, so the main thing was look into it, that how this condensate on the lower part of the tube can be decreased or can be reduced. So obviously, then this condensate, it has its dependence on so many properties. For example, what kind of tube geometries we are going to use. Once we talk about tube geometry, then this could be the height of these fins, this could be spacing between fins, or this could be the thickness of the fins. Okay, and also, this is greatly dependent upon the thermophysical properties of the fluid which we are going to use. For example, if we are going to use water, which generally has higher surface tension comparing to the refrigerants, it is going to produce a higher level of condensate retention. So in general, if I would let you know, these are the tubes which are going to be used in industrial condensers for a long time now. So we still have, these two-dimensional integral fin tubes going to be used in many of the industrial condensers. Although there are simple plain tubes, but some of the industries, or maybe in Europe, you would be able to find many of the industries, they are using such kind of integral fin tubes to be used in surface condensers. Okay, so if we try to look into the history of the experimental work on two-dimensional integral fin tubes, then it has a lot of history. So you would be able to get some of the earlier works presented by Katz and Geist in 1948, and Batty and Katz, they are well known in this pioneer work as well. So 1948 would be the era where you would see that there was a start of some of the experimentation on the integral fin tubes. But when we just start collecting the data, and we start looking into all of these studies, so one thing which you realize, that all of these studies have reported some good enhancement in terms of heat transfer when we compare them with simple plain tubes. But some of the problems are there as well when we try to interpret such kind of data which was presented like half a century ago. Then this is difficult, because not a lot of parameter discussion is given there, you wouldn't be able to get more information that what kind of measurement techniques they used and what was the accuracy of such kind of data, okay? Because once we are doing experimentation, so we can go for the calculation of convection heat transfer coefficient by direct measurements or by indirect measurements. Okay, so now if someone is going by indirect measurements or indirect calculations, then this would be really dependent upon the model or what kind of methods was going to be used there. Okay, so if there is no such information provided, then it really becomes difficult to judge the accuracy of the data. So what was done later, some of the data that has been reported by various researchers with some good accuracy, this was collected, and this data was used for comparisons with different models or for the development of further models. So if you see, then this data was reported in 1985 on some of the steam by Vinorci, but this has direct measurements, so this has good accuracy. Similarly, at Queen Mary University, many of the groups, main group was working on condensation heat transfer, and many of the researchers participated in that work, like Dr. Briggs and his co-workers. Then Dr. Rose, he was actually heading that group by that time, and many people did their PhD under his supervision. So he collected a lot of data, which was accurate one on different geometries. So here you see that we are going to get some of the data that is listed here for over 40 tubes and geometry combinations. So these symbols, you would see that later on I'll be using them into my figures so that we can make some of the comparisons as well. And one thing you should note here, that the data I'm going to present, this is just for low velocity saturated vapors, or maybe you may say that we are just going to consider like free convection heat condensation heat transfer. I wouldn't be going to look into the forced convection one, although there is a lot of work presented there, but this would be the part of maybe another talk. So here you see that we just want to look into that if we are going to look into the low velocity saturated vapors and the condensation, free convection condensation, then what experimental data we have, and then what is the progress on modeling when we talk about in terms of mathematical models. So what is the progress on that? So this is the data we are going to use. So when we talk about enhancement for integral fin tube, so what does that mean? What do you mean by enhancement? So enhancement, we can define it as the rate of heat transfer by a fin tube divided by the rate of heat transfer by a simple tube. So when we talk about a simple tube, then the outside diameter of the simple tube should be equal to the outside or the base diameter of integral fin tube as well, so that we can keep those diameters same in order to define the enhancement ratio. Okay, so once we are going to define enhancement ratio, one thing we need to make sure that can you hear me?
Yes, we can hear you, but some of the people has an open microphone.
I mean, should I carry on then?
Yeah, we can hear you and you can go on. Okay.
Okay, thank you.
You're welcome.
Okay, if there would be any problem, please let me know. Okay, thank you. Okay, so this is what I'm discussing here, that how can we define the enhancement ratio. Enhancement ratio, this is the rate of heat transfer on the fin tube divided by the rate of heat transfer on a simple plane tube. and we should take them at the same delta T. So what do you mean by delta T? This is the tube wall to the vapor temperature difference. Okay, so these are the important parameters. This is how we define enhancement ratio. So for enhancement ratio, later on I would be showing you that when I will be making this comparison, with the pin-fin tubes. So relatively so far, the experimental studies which are available on the integral fin tubes, these are the important conclusions that we can draw. Enhancement ratios are generally higher than the increases in the surface area. Okay, although the condensation of steam, for the case of a condensation of steam, it is not always the case, and this could be otherwise. And also we are able to define some of the optimum fin spacings and fin thicknesses for different fluids, because the properties of fluids are very important. But for integral fin tubes, now we can define optimum fin spacing, especially for steam, for ethylene glycol, and for many of the refrigerants. The third important thing is that enhancement ratios increases monotonically with fin height in most cases. Although once again for the case of steam, because the thermal conductivity for that case, is really important when we are going to consider steam. And if we have a tube material which has low thermal conductivity, then we must have to consider the fin efficiency effects as well. And also, the enhancement ratio decreases with fin thickness, since thicker fins with fixed fin spacing result in reduced fin density. So these are the important results that we can draw from experimental studies on integral fin tubes. Okay, so the surface tension effects, which are really important for the drainage process, because once we have condensate on the tube, so earlier, this was only considered that the drainage of condensate from that tube is by gravitational force only. Okay, so if you look into the model which was given by the Betty and Katz, they were just considering the effect of gravity. But later on, this was actually when a lot of research was done, so the effect of surface tension was identified playing a very vital role for the drainage process, because the fluids which are going to have higher value of surface tension, they have the potential to contract the fluid together. So that is why the surface tension effects were really important. And I would be presenting some of the models, especially given by Honda et al. And Briggs, those would be incorporating the effect of surface tension. So now you see that when we talk about this condensate retention on the lower part, so it becomes really important to define the tube area into two parts. So the first area that you can see on the upper part, this is the active area, where we can have heat transfer. And the lower part that is going to contain, condensate, this will be, the passive area, because due to the condensate, we wouldn't be having the rate of heat transfer up to the desired quantity, or this will be completely blocked, especially if we are dealing with the steam. Okay, so in order to define that area, we go for a flooding angle. This is known as condensate retention angle, which is generally in different calculations or different modelings, phi f, we can present it like that, and this is the formula for integral fin tube to predict the condensate retention angle. So once we have this condensate retention angle, based upon this condensate retention angle, we are able to make some heat transfer models, and by using this condensate retention angle, we can actually divide that tube into two parts, and we can only consider the active area for heat transfer. So this formula here, which you can see, this was given by, actually the similar formula was reported by different researchers. First, this was reported by Rudy and Webb in 1981, and later on Hounda and his team, his co-workers, they reported the same formula in 1983. And this is the beauty of this formula, is that this is analytical formula, which accounts for the effect of surface tension and gravity for the drainage and condensate tension. So if we, compare this equation or retention formula with the experimental work, so you can see it really gives a very good agreement with the experimental data. So that is why in most of the theoretical investigations later for the full-fledged heat transfer model, this basic condensate retention model is really popular to be considered. Okay. So later, we talk about the complete heat transfer model. So one of the important model for the complete condensation heat transfer was given by Hounda and Nuzu in 1987. Okay, so this model is a very important model. This model is basically based upon some of the numerical solutions of the governing fourth order differential equations for the condensate film thickness. And this model also considered the effect of surface tension and gravity. Later, a more, a simple model was reported by Rose in 1994. So this model also, accounts for surface tension and gravity effects. And the approach that was used, this was dimensional analysis to account for the surface tension, drainage effects, and also to incorporate the gravity effects. So if you look into the equations of these models, these are relatively simple and easy to adopt. So that is why it has a lot of adaptability. Here you would see that some of the data, which is for steam, it doesn't fit within 25% with the model. The reason is that because for the cases of fin, if it is going to condense on some kind of tubes which are made of material with low thermal conductivity like brass, then fin efficiency effects are really important. So later this problem was solved by Briggs and Rose in 1994, and they incorporated the fin efficiency effects into their model, and you can see that this problem was sorted out, and the low thermal conductivity or fin efficiency effects can be incorporated, and the modified model was working really great. So this is the one very well-known model that is generally used by design engineers and researchers in order to optimize integral fin tubes later. Okay, so the next part of my this is about the three-dimensional pin-fin tubes. Okay, so later, maybe in 1990, we get some of the data, experimental data. So this was some random data reported by Scatme on pin-fin tubes. Okay, so these are the three-dimensional tubes. Now you can see that how can we make these kind of tubes by making simply a cut on integral fin tubes. So anyhow, such kind of tubes reported some good enhancement when we compared them with the integral fin tubes. Okay, so there was no systematic data. So then, later this was considered like in 2007 that we should go for some of the systematic approaches so that we can get some good data and we can make some parametric studies. So in order to do that, these 12 tubes were selected where you would see that systematically the thickness, spacings, and same things were varied in order to get some systematic data. And whatever the results for enhancements were there, they were compared with integral fin tubes. So you can see by the colors here that these colors are going to represent the equivalent integral fin tubes to the corresponding pin fin tubes. So here we can compare the things. Like for example, in most of the cases, you would see that the heat transfer enhancement would be much more comparing to the heat transfer enhancement for the case of integral fin tubes. Okay, so here you see that what are the reasons for this kind of enhancement. Once we have these pin fin tubes and we compare them with the integral fin tubes, so you can see that there is a lot of reduction in condensate retention on the lower part of the tubes. So once there is a reduction in the condensate retention, so obviously we will be having more active area. But frankly speaking, strictly this wouldn't be only depending upon the condensate retention, because it is also dependent upon the available area on the upper part. Okay, so if we are going to make the spacing much higher, okay, so then might be we can reduce the available area, and this can reduce the rate of heat transfer as well. So the first challenge when we go for the pin-fin tube, three-dimensional pin-fin tubes, we have to come up with some kind of model that with the help of that model we could predict the condensate retention, right? As we had the model for integral fin tubes. So once we compared, the retention angles on the pin-fin tubes with the model presented by Honda, so you could see that it doesn't provide any agreement. So later, Ali and Briggs in 2012, they presented a semi-empirical model that was modified model of Honda et al. And this was a semi-empirical model, and we sorted out that problem, and condensate retention can be predicted on these tubes. Okay, so the final thing so far we have for condensation heat transfer of pin-fin tubes, we now have a model that can predict the condensation heat transfer on such kind of complex three-dimensional pin-fin tubes. So in order to develop that model, we used or we divided our tube into two different parts. For example, we used horizontal tube equations, and we used flat plate at angle phi on a vertical plate. These are the equations that were used, and you can see here that tube was divided into 5 different parts. For example, pin tip, similarly pin flanks 1 and pin flank 2, and pin root 1 and pin root 2. And for all these different parts, we came up with some of the fundamental equations for rate of heat transfer, and we combined them in order to come up with complete model. So once we were done with that model, so you can see that it gives a good agreement with most of the available experimental data. So at least we are at the moment we do have a good model for free convection condensation heat transfer on pin-fin tubes, and this is the way forward where we can go for different works as well, and a lot of working is still under process for free convection condensation in order to optimize different geometries and things. So in a conclusion, we can say that for two-dimensional integral fin tubes, the mechanism is relatively well understood, and we have good models for retention and for heat transfer, as long as we are going to talk about the two-dimensional tubes. But once we come for the more complex three-dimensional pin-fin tubes, so these tubes have shown really great potential for condensation heat transfer. Okay, so now the model is available, and based upon that model, we can actually optimize different geometries that can be used for different kind of applications for a number of fluids. And the semi-empirical model that is reported by Aline Briggs 2016, it shows some good agreement with experimental data, and this could be used for further optimization of pin-fin tube geometries. So thank you very much for your patience and your attention so far. So I think I'm still in time. So thanks once again. If you have any questions, you're most welcome. Please go ahead.
Okay, thank you very much for a nice talk. Please, questions or comments? Okay, if no questions, please thanks speaker again. And
Thank you very much.
the next speaker should be introduced by Turkish counterpart.
Good morning, everyone. Dr. Bakshir, good morning to all the colleagues in Turkey, and good afternoon to all colleagues in Kazakhstan. Let's shift the gear towards plant genomics, plant sciences. I feel immense pleasure to introduce Dr. Khurram Bashir with you all. Dr. Khurram secured his PhD degree from University of Tokyo in 2007. Later on, he served the same university as a research scientist for 6 years. Since 2013, he is serving RIKEN, Center for Sustainable Resource Science, Japan, as a research scientist. RIKEN is well familiar to all plant scientists around the world because of its brilliance, integrity, high quality research, and above all, contribution to science and agriculture. Dr. Khurram is one of the scientists who make this institute great, outstanding, and outperforming. Dr. Khurram is working in the area of plant genomics since last 2 decades. His research has been published in world prestigious journals like Nature Communication, 2 times in fact, Nature Journal, Journal of Experimental Botany, Scientific Reports, the Planet Journals, and the list is long. So today, he will talk about novel aspect of drought stress tolerance in plants. So with the excitement and pleasure, I would like to invite Dr. Khurram for his talk. And recently, I talked to him. He was trying to connect with us, and I hope he is connected. Dr. Khurram, over to you if you're around. So he's using this system for the first time. So for a moment, we can have a
Hello, Allah Bakshoja.
yes, sir.
You wanna try to share your screen?
No, Dr. Khurram is trying to connect with the system. So because yes, sir.
He need to click on the link. That's it.
Oh, actually, he thought that the lecture is 1 hour late, to be honest. So I'm just receiving his message. So is it possible if we shift the participant, if we have the other one with us right now?
Let me ask the other speaker is ready. Okay. Professor Tolga Murat, are you there? Yeah. Professor Tolga?
Talgat Muratovich, вы с нами?
Yes, I'm here. Watch us.
Are you ready?
Professor Tolga, if it is possible, we can start with your speech and then continue the next speaker because of this speaker right now has a problem.
Okay.
And we
Sorry,
need to shift. Okay.
I just
We need to shift.
prepare. I thought my talk will be the next one and prepared for this, and little bit was out of
No
discussion.
problem. We can wait. We can wait. No problem.
Okay, now I'll share screen.
Uh-huh.
This one. Okay. Do you see my slide?
Yes, we do.
Okay. Thank you very much. I'm a little bit unexpected for me.
Professor
this
Tolga,
might-
please introduce yourself.
Okay. I graduated Novosibirsk State University in Russia. After that, I got PhD degree there, and after that, I worked as postdoctoral research associate in Japan in Tohoku University, Sendai, also in University of Central Florida, in USA, and also I have experience working in China. I worked in Guangzhou City in South China Normal University. Okay, and now since it will be soon 9 years as I am invited professor in Gumilev Eurasian National University. I joined to Eurasian National University in 2012. Okay, my research interest is quite wide. I am theoretician, make the modeling of properties of different materials, and current talk is the result of my cooperation with Japanese researchers from Tohoku University. The title is Magnetostriction in iron gallium alloy doped with nickel and praseodymium ions. And first of all, what is magnetostriction? Magnetostriction is quite discovered by classical physics by James Joule in 1842, and the effect is the change of the. Initially, it was discovered the effect of change the shape of ferromagnetic sample under effect of external magnetic field. And currently, there are known a lot of different magnetostrictive effects. There are direct effects and inverse effects. First one, Joule magnetostriction was discovered by James Joule, and it changed sample dimensions in the direction of applied field. And inverse effect is the change of magnetization due to applied stress, and so on, and also change effect on the magnetocrystalline anisotropy, and so on. And you
Professor
can see
Tolga,
yes.
Excuse me, we cannot see your other slide pages, and
Really?
you need to share your screen directly. Yes.
Okay.
Just cancel the sharing and then
Okay.
start again.
Start again. Okay.
And share it directly screen, not the page. Screen direct.
Screen.
Mm-hmm. Screen one. Screen.
You change?
Not yet.
Oh, okay. Once again. But system offer me to change some particular window. For example, I share
yes, and just select screen one. That's it. Screen or. Yes, now we see, and change the page, please. But we cannot see, and you still sharing your page.
Okay.
Can you make it full screen?
Wait a moment.
Start presentation.
I don't understand how does it work. I see the
Okay.
desk, PowerPoint. Do you see my screen? I share screen number 1.
Yes, we can see.
You see change, yes?
Yeah, yes, sure.
Okay, okay. This is summary of different magnetostrict effects. I will focus my attention on the Wheeler effect. This is for this application. Problem is, sometimes for people install in some buildings or somewhere else sensor, for example, for security. And this sensor don't need so much energy. And the simplest way is to put there the battery. But battery you need to change from time to time because of the charge leaking. And you need, and for this purpose, also it is necessary to have some source of energy, but you don't need so much energy. The amount of energy should be very small. And for this purpose, magnetostrict effect is quite usual. How it works? Because under stress, the direction of magnetic field changes. And since it changed due to the Faraday effect, it generates some current. And this current can be used to charge some capacitor, for example. And just keep this capacitor charged during quite long time. And this is enough. You can install, for example, sensor somewhere and forget about this for a very long time. But one condition, there should be source of vibrations. For example, no, but some small vibration is enough. For example, all the buildings on some have experienced some vibration due to cars or trains going outside and so on. For example, in Japan, which is no problem because the earthquakes happen from time to time. And this is why this problem is important. And this is energy flux between different subsystems. Okay, and for this purpose, we can use different materials. But they have some advantage and disadvantage. For example, the most effective from the energy point of view, this is piezoelectric materials. But they are experience depolarization, they are brittle and so on. But magnetostrict also have some advantage and disadvantage. And this is summary of current materials. The most popular is alloy. This is alloy of iron and gallium, which I am studying. This is very good, cheap, non-toxic, and so on. But magnetostrict coefficient is about 5 times less than for terphenol. Terphenol is alloy of terbium, dysprosium, and iron. Very good material, but it uses quite expensive rare earth elements. And you see, according to the chemical formula, about 30% of in this compound contain rare earth elements, which is not good from economical point of view. And the idea is how can we modify galphenol to improve its magnetostrict effect. And this is some experimental results showing the change of magnetostrict coefficients with the gallium concentration. You see it has two maxima. And one is about 20% of concentration, second one is about 27. And later I will explain what is the effect. Effect is this alloy experience some structural phase transitions. This first maximum corresponds, this at about 20%. It corresponds to disordered alloy of disordered solution of gallium in BCC, body-centered cubic lattice of iron. And after that, there is phase transition, and at this concentration, there is not this is not alloy. This is ordered structure, and this summary of all possible, all found structures in this gallium iron alloy. The first maximum at 20% of this is 20% of gallium is so-called A2 structure. This is, you see, this body-centered cubic structure with partially filled with gallium or iron. And 25% of iron. Sorry, I didn't put. This is DO3 and L12 stable configurations. And this chemical formula is iron 3 gallium. And most DO3 is metastable, but it transfers to L12 at temperature about 1000 Kelvin. And first of all, this is experimental and theoretical picture. And this at zero temperature, this 5 picture is the result of modeling. Left is the summary of experimental results. This phase diagram in iron gallium alloy, where we work in here in this region with A2 structure, and at 25% of gallium concentration with phases DO3 and L21 cubic phases. Okay, this is why experimentalists in Japan asked me to calculate this, because sample preparation, especially with rare earth elements, is very difficult and expensive. And computational methods can accelerate this problem solution. Okay, let's a little bit about theory. This is how we calculate magnetostrictive constant. And this one is derivative of magnetocrystalline anisotropy energy with respect to the strain. What is magnetocrystalline anisotropy energy? This is a difference between energy in Z direction. Okay, sorry for non-specialists. I'm forced to use some quantum mechanical terms, since I thought that my talk will be initially on the special physical section, but since this is plenary, I don't know how to make it simpler. Magnetic crystalline energy is energy when magnetic moment directed in some XYZ direction, minus energy when this magnetic moment directed along Z axis. And this is quite a very small value. You see, this result of modeling shows that this energy is about, in order of magnitude, about 1 milli electron volt per atom. And it requires extremely high accuracy calculations. And in denominator of this formula, this is second derivative of total energy with respect to the tetragonal strain. It gives the tetragonal share modulus for this system. And first of all, this is explanation how we calculate the theoretical distortion. But okay, let's skip this. And since we need total energy and energy of magnetocrystalline anisotropy, we should use some very exact methods of calculation. This method is, I use the density functional theory method. This is one of the most powerful computational methods. It allows us to calculate quite large systems. And also the magnetocrystalline anisotropy calculation implemented here. And we use the VASP, so-called Vienna ab initio simulation package. This is commercial program. I think this is one of the best in this field. And, oh, sorry. Yes, this is a result of our simulation where we estimate the accuracy of our modeling. And this, on the left side, there is a comparison of different calculations and experimental result. You see that quite good agreement between theory and experiment. And also we compare directly, we can compare directly the value of magnetostriction constant. And also we can directly make comparison for tetragonal shear modulus, this elastic modulus. It also was measured experimentally. You see this accuracy is very good, and at this fixed concentration of gallium, it is on the curve, and it's on the experimental curve. Okay, this is results of our modeling for lanthan series elements doping of galphenol, and this I cannot extend this series of rare earth elements for other elements because some technical reasons in computations. But this part, for first 4 elements, we got the quite good qualitative agreement between theory and experiment. And okay, what is the origin of high magnetostriction in iron gallium alloy? Okay, this is high magnetostriction is originated from the rotation of magnetic moment. Magnetic moment can be rotated when the coupling between electronic orbitals of neighboring atoms should be quite small first. The second one, and we need the high density of states for d states for iron. And here's comparison of density of electronic states for spin up and spin down, comparing with the bulk iron. You see that for states with spin up, the density of electronic states is few times larger in galphenol alloy in comparison with the bulk iron. And second one, for free rotation of magnetic moments, we have to calculate what is the nature of coupling between these states. This we use so-called crystal orbital Hamilton population analysis. This analysis can show this chemical bonding is bonding or anti-bonding. Anti-bonding means that if we have anti-bonding connection between different electronic states, it means that this spin can rotate freely. And for example, this method was applied to explain why this series of elements are ferromagnetic. You see that since this part, we could have quite high density of electronic states in left region. Left region corresponds to the negative values. This corresponds to the antibonding connection between electronic orbitals. And you see for the manganese, iron, cobalt, and nickel, there is quite high value of electronic density of states with antibonding. While for other elements, connection is bonding. And this is why this ferrum gallium alloy possesses high magnetostrict response. Okay, we calculate this using this method. We calculated the nature, or calculated the crystal orbital population analysis, and here I will summarize what's the effect. You see that experimentally it was found that, for example, nickel doping of galphenol that has no any effect. It does not improve the magnetostrict response of galphenol alloy, while rare earth elements, praseodymium, increases it significantly. And this, from this picture, we can explain why this effect takes place. You see that for galphenol, this is green line, the electronic density of states is quite large, quite high value at Fermi level. It explains why the galphenol alloy has the so large value of magnetostrict response. And for praseodymium doped galphenol, this value increases significantly, while for nickel doped, no change. And this is for spin up. For spin down, these bonds corresponds to these bonds are bonding and make this connection. This chemical bonding makes the system stable. It is not involved to the magnetostrict effect. And okay, we have just 5 minutes. I should finish. And these conclusions that we studied the magnetostrict properties of ferrum gallium alloy and found that the DD electron coupling has bonding character for nickel doped alloy and anti-bonding for praseodymium doped alloy. Okay, thank you very much.
Thank you, Professor Tolga, for this nice presentation. Do you have any question to Professor Tolga? Any question? Okay, so Professor Tolga, may I ask you that do you have any application for using this research in any product yet?
My Japanese colleagues do something in this by the experimentalists. I'm theoretician and I do just modeling. This is used, as I said, for sensor, for ultrasound sources and so on. We just want to improve properties of this material and also improve the quality of devices which are used using this material. In principle, this is used. Problem is to reduce cost of production of this material using the cheaper elements like iron and gallium, and also if you use terphenol, as I said, it contains about 30% of rare earth elements. It makes this quite expensive. But if I will use small amount of rare earth elements in iron gallium alloy, solubility of rare earth elements in iron gallium alloy is very small, less than 1%. But effect is very huge, experimentally found.
Okay.
But from point of view of theory, it is not clear why. First of all, we need to explain. Second one, predict something new, maybe, to make the search of new materials faster.
Okay, I see. Thank you for this nice presentation again. And I think we need to shift next speaker. And
okay, yes.
I think, yeah, so here is your turn, Professor Tolga, and excuse me, Professor Allah Bakış. Are you there?
Yes, I'm here. Thank you so much. Now we have Dr. Khurram Bashir with us. I already introduced with that. Sorry for that.
If you want, you can make quick summary for introducing him.
Yeah. Okay. Thank you. I take again. I'm very excited and pleased to invite Dr. Khurram, who completed his PhD from University of Tokyo in 2007. He served the same university for 6 years. Since 2013, he is serving RIKEN, Center for Sustainable Resource Science, Japan, as a research scientist. He's very familiar scientist in the area of plant genomics, who has published in prestigious journals like Nature Communication, 2 times they published, Nature Plants, Scientific Reports, Journal of Experimental Botany, couple of times they published, plant journals, and these are very prestigious journals of plant sciences, and their list is long of publication. So he'll talk about the novel aspects of drought tolerance, stress tolerance in plants. So I would invite Dr. Khurram for his talk. Over to Dr. Khurram.
Thank you very much. Can you see my screen?
Yeah, Doctor, we can see now.
Okay. So sorry for being late. So, but without wasting time, so we will start that novel aspects of drought stress tolerance in plants. So we know there are various kind of stresses, and if you see this map, you can clearly see that the area where I am sitting to the area where this conference is organized, everything you can see in red color. That means that these countries are severely facing water shortage, water stress, either way. So it's very important for the crop scientists, plant scientists to tackle these problems. So there have not been research, so I would not go into very detail what kind of techniques normally people use. So what could be new strategies? So being from a plant scientist perspective, so what could be new technologies like GM technology or other things, but what are the novel aspects of these things? So I have characterized these new strategies is uncharacterized genes, for example, identification and characterization of genes which have not been utilized so far, and novel promoters to regulate these genes. And at third stage, small open reading frame, these are the genes, basically genes, which are not considered as genes because these are too small. The scientists thought for a very long time that these are not functional. And then chemical screening. So I will take 1 or 2 examples from each aspects because I am working on all these aspects, and it's not possible to go into very much detail, but I would try to introduce, okay? So in the first report, uncharacterized genes and how to identify these uncharacterized genes, for example. So we know that this RIKEN group, and if you are familiar with the drought science, Professor Shinozaki, Professor Seki, so they have been working on these aspects for the more than 20 years. But sometimes we neglect some things which are not very quite straight. And So, and the different aspects of the drought has been characterized. You can see that a lot of work has been done by various groups in the world, like identification of water channel transporters, transcription factors, protein kinase, phospholipids, ABA biosynthesis, and other hormone biosynthesis, proteases, key enzymes for osmolyte biosynthesis. A lot of work has been done. However, when I started work, so I realized that some factors are missing. So these factors were missing, that we don't have actual data of the plant grown in the field conditions or near field conditions. Number one. Number two, we have missed the data that are dissected into tissue specific manner. I mean, in root versus shoot, for example. So we first try to introduce a new system in which we can grow plants, and then we may be able to stress these plants with water shortage, for example. Other stresses are also possible. And we have also very customized microarray analysis, which is still very valid in the age of RNA-seq. Our microarrays still have some advantages on RNA-seq technology because we have covered the whole genome. So it's same coverage as of RNA-seq and with much more efficiency. Device that we used a specialized kind of soil. Then we grew plants in these soil, and then we subject it to drought stress. These are different stages of drought stress. For example, when we stop watering and completely dry the pot, then you can see the plants are growing up to 5 days. They are quite happy. But from around 7 days, they start feeling distress. This is visible symptoms. At molecular stage, 5 days, plant seems very healthy, but I will show later that they feel and they sense that something is coming, just like winter is coming. You have heard in Game of Thrones. So they sense that the drought stress is coming. They know beforehand. How they know? From roots. Okay, so I will skip some slides. So if you see here that plants are very happy up to until 5 days of drought stress, even 7 days of drought stress, they seems quite healthy. You can see that the water is growing, root fresh weight, shoot fresh weight is increasing up to at least up to 5 days. They seems quite healthy, and they also shift from one vegetative stage to flowering stage. The water availability is decreasing very steadily day by day. And when we see at molecular level, we know that although 3 and 5 days, the water seems apparently look very healthy, but there are a lot of transcriptomic changes going on in the root and the shoot. And if in this initial period, if you see, for example, 3 days, you might notice that the number 497 genes upregulated in root tissue is much more than compared to the shoot tissue. So this means that, and it's also apparent, and this data also confirms that roots, they sense drought much before the onset of the drought and much before the shoot tissue. So we have focused on this root specific genes and we identified approximately 1500 genes which were never reported to be related to the drought stress. Among these are different functional genes, and we have also used one gene as a novel promoter to regulate the expression of other genes. Okay, so and ABA and the synthesis, ABA is a very important aspect, hormone for the drought stress tolerance. And even in this respect also, if you see this the changes of the expression of the genes in the roots, they are much more evident as compared to the shoot tissue, particularly during the 3rd and 5th day. From 7th day, they are comparable to some extent, and some genes are much more expressed in root tissue compared to the shoot tissue. So we have focused on a lot of these genes, so it's not possible to present all of these genes. And when we say the metabolomics level and transcriptomic on whole cellular level, you can see that how progressive this is, that how the significantly progresses with time and very steadily. So if we can counter it, so we can have much more better opportunities to regulate the expression, metabolome of the genome, and not only the expression of the gene, but metabolome of the whole plants, which can result in the better plants, which can better withstand with drought stress tolerance. These are the few examples of the novel genes whose function have not been characterized yet with respect to drought stress. Some genes are maybe used as a marker for the drought stress tolerance. For example, if you see this sweet 15 expression, which is marked by the red rectangular, you can observe that this gene can be used as a marker for the drought stress. Even plants look very healthy, but if you check the expression of this gene, you can guess that drought stress is affecting water availability, is somehow compromised, and plant may shut its growth in future. So this gene is significant, so equally effective both in root and shoot tissue. So we also identified some novel genes, and we make overexpression plants of these genes, all 4 genes. These are first thing you see that the expression of all these genes. So these are transcription factors and enzymatic reaction related genes. You see that the expression of these genes is specifically upregulated in root tissue, not changing in the shoot tissue, which is shown on the right hand. So left hand is root tissue shown in red. So you can see that the expression of genes is very specifically upregulated in root tissue. And when we make overexpression of these plants, they are all tolerant to drought stress. So I am not showing here, and the figure are not showing. The second thing we can, as I mentioned, that plants may encode much more proteins, peptides than we think. So these SORFs are annotated, non-annotated genes, which may encode small peptides, typically less than 100 amino acids. And Hanada et al. They reported that approximately 8,000 SORF are in Arabidopsis, and in rice, up to 48K SORF have been predicted. It's very surprising because the number of the genes in rices are estimated about 30K. So these are even much more than the predicted genes. And many of these are functional. So many of the genes, it's not possible to show all the data here, but many of these SORFs are very strictly regulated by one or more stresses. So we have published some data on metals also, so I'm not showing here. And we know that these kind of these kind of peptides may be involved in signal transduction to gene expression regulation. And if we make overexpression plant for these very novel genes or peptides, so we may have regulate the drought stress tolerance. And we also check the expression of these genes in a tissue-specific manner, and there are many SORF which are upregulated in shoot tissue specifically. So these are, and we make overexpression plants, homozygous independent lines, and of various lines. So I am only showing here 2 kind of OX plants. We have some code names like 220, SORF 220, and SORF 40, for example. So you can see that these plants perform much better under water limiting conditions. The wild type on the left hand shown by the red rectangular, you can see that plants die when we cease watering for around 13 to 15 days. So plants die, but transgenic plants, you can see that they can grow, continue growth. There are varying degree of growth in different lines, but as a general, you can see that 4 independent lines for 220 and 3 independent lines for SORF 40 OX plants. You can see that the plants are surviving, and below the survival percentage may be as high as 80%, 70 to 80% for these lines. So we also have transcriptomic and other data we are characterizing. So I am just presenting this data as an example that how we can utilize different resources which are not even annotated to make plants which can perform better under water stress conditions. I'm not going to show the complete molecular analysis, but we are working. We have RNA, microarray data, transcriptomic data, and some other evidence that these genes contribute to. So I want to stress a very important strategy, that is chemical screening strategy. So this is quite new. So, and this can be divided into, and this is quite new for abiotic stresses. We know that biotic stresses, for example, insecticides have been used for a very long period of time. But you have not heard a medicine for a drought or salinity or something similar for abiotic stresses. So in this era, for the last few years, so scientists have shifted towards chemical screening strategy or medicine for plants for abiotic stresses. And this, you can see that these are three kind of, we can simply divide in three categories. For example, phenotyping against a chemical library. There are many chemical libraries available, which are, some are as large as containing 25K compounds, like 25,000 compounds. And you add compound one by one, and you check that which compound is making drought tolerance. There are some biosafety issues. For example, if you identify a compound that is adding to the drought stress tolerance, for example, but you don't know if it is safe for humans or environment, you don't know. So these are concerns. They might or might not be safe. The second screening is, that is typically developing a chemical. So you specifically design a chemical for different plant characteristics, and then you check that if they really increase stress resistance. For example, we published in 2018 in Nature Communication in it was from Tohoku University and collaboration. So for example, jasmonate reception, so you can rationally design antagonists. And the third part, which we are focusing most, so this is the chemicals already metabolized by plants. For example, acetic acid, all land plants synthesize acetic acid. So what if you add acetic acid to the plant instead of making them GM? And comparing both strategies, for example, you make GM plants which are making more acetic acid, and you add external acetic acid, and then you check the compare the both strategies, and then if non-GM strategy is working, you need not to make GM plants, and it's quite cheap. It's already we know that healthy for plants. So the original paper was published by Kim et al. In Nature Plants. So I am co-author for this, so I am not presenting that paper. We are also working on different aspects of this. For example, the original paper which covers the epigenetic regulation of drought stress tolerance was published. We also adopted two different technologies again. So for example, we make OX plants, and we also found a very novel promoter based on our microarray transcriptomic data, which I presented in the beginning of this slide, that for example, TSPO proteins, this is, you see that this is very specific to drought stress. The expression of this gene is regulated very specifically by drought stress. It starts from third day. It's very significantly high compared to the 0 day. So the level scale is slightly different at the bottom. So you can see that this is very specific to drought stress, so it might be very useful. And we make the OX plants for the genes which make more acetic acid, for example, pyruvate decarboxylase 1 and ALDH87. So we first check the expression of these genes. We checked how many genes are there and how many might be involved in acetic acid production, specifically under drought stress. So you can see that ALDH87 is most affected by the drought stress. Its expression is significantly upregulated under drought stress compared to the other ALDH genes, and PDC1 is the only gene whose expression is upregulated in both in root and shoots under drought stress. So we selected these two. So I am skipping some data. to save time. So this is. So we use PSPO promoter, PDC1 and DLDH2B7 OX plants, single OX plants, and the transgenic plants which express both these genes. We know that the PDC1, the subcellular localization was not reported before, so we also check the subcellular localization, which is the cytosolic. We know that the PSPO promoter, so this is promoter gas analysis. You can see that this is very strictly regulated by the drought stress. And here, why it's not expressed, because this is these plants were not grown under drought stress. This is, we just check if the expression of these genes changes with the developmental stages. So you can see that the expression is only observed in during flowering, and people working on drought stress already know that this process is very much similar to drought stress, because plant desiccates during flowering. Okay. And when we grow these plants under drought stress, you can see that from third day, this expression of the gene starts, and at 7 day, the maximum expression can be observed. 5 day, you can see.
Dr. Khurram, I think your mic is off again. Can you turn on your?
You can hear now?
Yeah, it's okay now.
Okay. Okay, so you can check that this is QRT PCR for the OX plants. So you can see that we have transgenic plants, different independent lines. These are single transgenic lines, for example, here. And PDC1 plus ALDH2B7 means that we have double transgenic lines, which are expressing both these transcripts under the control of TSPO promoter at the same time. So these analyses show that these plants have more can produce more acetic acid, and then we check if these are really tolerant to drought stress. You can see that these transgenic plants are perform really better under drought stress. Under conditions where are the wild type plants, almost all the wild type plants die. Majority of these plants can survive. So this varying level of survival, which is very natural for the people working with plant biotechnology, so that we can get good survival ratio, both for single and double transgenic lines. So, and part of this data was published in Nature Plants, and rest was published separately. And as I mentioned, that transgenic approach is very common, although we utilize novel genes, we utilize novel promoters, but some people somehow don't like GM technology. So there might be other alternates. For example, instead of making plants which make more acetic acid, what if we add acetic acid externally? So, and check different aspects. For example, we check metabolomics. This is GC mass analysis. So we observe that when we add, for example, 10 millimolar acetic acid to the Arabidopsis plants, which are 2 to 3 weeks older, so metabolome is quite significantly altered. And for example, pyruvic acid, serine, homoserine, and glutamate, phenylalanine, and these elements enable plants to perform better under drought stress tolerance. They really show the drought stress tolerance. So they are tolerant to just like GM plants. And this expression, this changes in the metabolome is not only evident in root but also in shoot tissue. So, and we also confirmed that if we add labeled acetic acid, for example, if we add carbon labeled acetic acid, and then we detect what happens to this labeled acetic acid. So we just trace this, that this goes to TCA cycle, and this also goes towards sucrose, which indicates that gluconeogenesis is utilized for gluconeogenesis. In plants, gluconeogenesis is not normally discussed under normal growth conditions or under drought stress. This is not discussed. No one talks about it. This is a very novel aspect, that gluconeogenesis is normally important during seed germination and flowering, when plants utilize metabolize lipids. So, but we are reporting that this is also a very important aspect during the plant growth, vegetative state, and during drought stress tolerance. And this is the simple pathway. So I wanted to present it at the end so that we can see that what actually happens. So this is the pyruvate and it's converted to acetyl-CoA. This is a very normal process under drought stress, for example. So this, instead of going into acetyl-CoA, this pyruvate is converted into acetaldehyde. Part of it can be converted into ethanol and then came back. ALDH2B7 converts this to acetic acid, and then ACS enzyme that converts it to acetyl-CoA. So today I have very limited time, so I cannot show all the data, but we have characterized all these mutants, their performance under drought stress. These mutants are except ACS and ALDH, so for example, PDC1 and ALDH2B7 mutants are sensitive to drought stress. And so NMR data also shows that this acetic acid, added acetic acid go to gluconeogenesis. So we know that TCA cycle and the glyoxylate cycle is significantly overlapping. I am not saying that they are occurring in the same place. TCA cycle in mitochondria and glyoxylate cycle is in peroxisomes. But they functionally, if you see that the synthesis of use of acetic acid, acetyl-CoA, and then citric acid, cis-aconitase, isocitric acid, until there, both cycles are very similar. But in glyoxylate cycle, what happens that isocitric acid is converted into glyoxylate and succinic acid. And this is much more carbon efficient compared to the TCA cycle, because you can observe here that in TCA cycle, 2 carbon atoms are lost. So here it does not happen. So, and this is finally converted into malic acid, succinic acid, fumaric acid, malic acid, and then gluconeogenesis to the reproduction of sucrose from the sugars from the acetic acid or citric acid. So this is very important. So our data shows that this process is very important for drought stress tolerance, not only drought stress tolerance, but also for other stresses. And if I summarize, based on the mutant analysis, some of the data I have not shown due to shortage of the time. So I'm just going towards conclusion. So this is the whole picture of the metabolism. There is some putative transporter. So we are also working on this. I have not presented data here. So acetic acid goes into this cell, and this acetic acid goes towards different, for example, chloroplast. It goes to chloroplast where ACS enzyme utilizes it for fatty acids synthesis. Then this acetic acid goes towards peroxisomes, where it is utilized for lipid metabolism, jasmonic acid synthesis, gluconeogenesis, glycoxylate cycle, of course, through this. And this is also utilized inside the cytoplasm to synthesize acetyl-CoA, which is very vital to the plant metabolic systems. So in summary, so basically I talked about 4 different approaches. Number 1, use of identification and characterization of novel genes, which have not been reported, and we reported that we identified approximately 1,500 novel genes, and then identification and characterization of novel promoters, for example, TSPO promoter, which is drought-specific promoter, and transgenic plants expressing acetic acid pathway genes regulated by drought-inducible promoter. They exhibit drought stress tolerance. And acetic acid itself significantly not only enhances the drought stress tolerance, but it also alters the metabolome and transcriptome in roots and shoots. And putative acetic acid transporter, which we have identified, it may be involved in acetic acid transport and distribution. And acetic acid and similar chemicals, we are currently using at least 3-4 chemicals which are I am not going to disclose today, but this is using as the example of acetic acid. We have very similar chemicals which are very cheap, which are safe to the human health, and which can be used as a medicine for the plants to enhance different characteristics. For example, drought stress tolerance, salt stress tolerance, cold stress tolerance, and even for the increase of the biomass. So this is very promising, and biotechnology is progressing in a good way, and to address the problems for plant breeding. Thank you very much for your attention.
Thank you, Dr. Khurram, for your comprehensive talk. We have a couple of minutes, actually 2 minutes. If you have a question, please.
Yeah, may I ask a question?
Burunu Zujan, please, go ahead.
Okay. Hi, Dr. Bashir. Thank you very much. This is very nice and informative speech. Actually, the drought stress is it's a hot topic in the world nowadays because of that climate change effects. So actually, I have a couple of questions, but maybe I can ask only one or two. The first, one of your study, you studied about root-based and shoot-based genes responsible for drought tolerance in plants. Actually, the droughts are plant receiving drought stress first by the roots, but the more profound effects is obtained in the above ground parts. So, do you think which one is the more logical strategy to screen drought-tolerant plants, looking for the root-based genes or shoot-based genes?
So both are very important, but if when I see my data clearly, so roots are very important for photosynthesis and metabolite synthesis. But problem is that roots shoot sense drought stress is much later stage, while root sense is much earlier. So root specific genes are much more important to give response. So for example, you can utilize the root specific genes, root specific drought inducible genes as a promoter to express your genes of interest in shoot, even in shoot tissue. So for example, TSPO and some other genes. So it's not important that we regulate the expression only in a root specific manner. But if we want to focus on drought stress, and specifically during early drought stress, during late drought stress, sometimes even the transgenic technologies fail because the damage is so much evident that plants cannot respond much. So in this regard, I think that the root specific genes are much more important because they can predict, they can sense the early.
Yeah, thank you very much. I have one more question. If we talk about the drought stress because of the climate change, the generally drought is coming with along with the heat stress. The plants not faced solely with the drought stress, but also at the same time heat stress also affecting the plants. So I think it's more feasible to study the combined effect of drought and heat if you are trying to develop a more climate resilient cultivars adapted to this the climate change conditions. What do you think about it?
This is very important, and this is especially very difficult also, both things. First thing that we understand that when plants try to respond to drought stress, they close their stomata to reduce water loss. And when plants try to respond to heat stress, they close their stomata and make a lot of water wastage, so to keep them cool. But as you said, that I fully agree that these two stresses are very much linked in the field conditions. And I have not presented data, but we are working on several chemicals which not only at the same time which all gives plants tolerance to drought stress and heat stress. And for this purpose, it's important these are not very linked to stomatal opening, which is very and ABA pathway, which is very common in drought stress. So we have to find some novel mechanisms where metabolome is specifically regulated, especially through gluconeogenesis. If you can gluconeogenesis, plants can perform much better even with closed stomata, and conserving even water, and then making some metabolites which can help plants to better perform under heat stress also. So these two stress are very linked, and there are many, we are working on this, and there are several, not several, at least we have one chemical which we have very good experimental data that the same chemical application, they can enhance drought stress tolerance as well as heat stress tolerance.
Okay, thank you very much.
Dr. Khurram, taking liberty, I would quickly ask a question. Your work of external application of acetic acid, have you applied to Arabidopsis? Is it limited to Arabidopsis, or are you trying to other crops as well?
Not only acetic acid, for other chemicals we have data. For example, for one chemical we have data for Arabidopsis, wheat, cotton, and rice and maize. So
okay,
and even also for cassava. So these chemicals, more than one. So we have not failed with any crop so far.
Okay, great. Thank you. And any other question?
Yes. Hello, thank you. It's a good presentation.
I think we have
a
to
very
stop this
interesting
discussion
issue. So,
because of
if
timetable.
if you understand correctly, I can see one of the slides where they have the commercialization of this technology, and where is it was the commercialization, this one, and what is the impact to the economy if you commercialize.
But for example, acetic acid, so my institute has a patent for acetic acid utilization, and one company is working in Japan to solve this for farmers. So there is good option for commercialization also. And some chemicals, they are already published, even for other uses already in use. So there are both ways. So commercialization is very much possible. We have patent for more than one chemical. My institute has more than one chemical patent. So, and yeah, one company for acetic acid is already working in Japan. So it's very much possible.
Thank you.
Okay, I think we are short of time. Dr. Khurram, thank you so much for scheduling, sparing time for us. Thank you for being among us, and hope to see you soon next year as well. Over to you, Dr. Murad Hoja.
Microphone.
Thank you, Professor Allah Bakış, and thank you, Professor Bashir, for this great presentation. We hope also waiting you for next year, as Professor Allah Bakış says. And Professor Tolga.
Yes, yeah, I'm here.
Yeah, it
yes.
is your turn.
Okay, let me introduce next speaker. It will be Dubek Kazuken. He graduated Eurasian National University. He got his master and PhD degree here at the time in Astana. But now he works in University of Michigan, in medical school of University of Michigan. And title of his talk is Ampk directly activates mTOR-C2 in responsible to energetic stress and promotes cell survival. Sorry if I pronounce the abbreviation incorrectly.
Yeah, that's fine.
Okay, please.
Thanks for the introduction.
Share your screen.
I'm going to share my screen. I think I need to give an access. This is first time for me to use this software, so I need to set up. All right. Could you see?
Yes, yes. Please change slide. We should check this. Yes, yes, good. Perfect.
All right. Thanks for the introduction. I'm Dubek. It is here 3:30 in the morning now, so it's very late to sleep, too early to wake up. I'm a postdoc in Finger Lab at University of Michigan Medical School. I'm gonna introduce my last publication, which is titled AMPK directly activates mTORC2 in response to energetic stress and promote cell survival. So our lab, the Finger Lab, is focused on does mTOR phosphorylation control mTOR complex function. So here, I think from the other field of the research, probably people may not know what's phosphorylation, what's kinase. These terms I'm going to use again and again. Phosphorylation is a reversible post-translational modification of the proteins. I'm talking about protein phosphorylation. So, which is the adding a phosphate group to one of the serine or threonine or tyrosine residues within the protein. Kinase is the enzyme which does the job, which transfers the phosphate group from ATP molecule to the protein. So our lab mainly focuses on this phosphorylation of one protein called mTOR, and how these phosphorylations affect the function of mTOR. Now, my main talk is gonna be focused on the energetic stress induced cell survival, how cells survive during energetic stress. Like mammalian cells experience diverse kind of energetic stress, like in hypoxia caused energetic stress, or tissue damage, or the newly formed fast-growing tumor cells in the core. Before the angiogenesis happen, cells experience energetic stress, and how cells survive under these energetic stress conditions. So, brief outline of my talk. I'm going to introduce AMPK and the mTOR signaling systems. These are the ones we study. And identifying mTOR protein as a AMPK kinase substrate. Then I'm going to focus on our new finding, AMPK associates or interacts with mTOR2. Then AMPK promote mTOR2 signaling or its activity. And AMPK increase TORC2 catalytic activity directly. Then I want to talk about the function of these axes, like AMPK, mTOR2 signaling axis. And I will briefly talk about the potential physiologic significance of this new axis. And lastly, what we have learned from a genetic knock-in mice we have generated in our lab. So what is AMPK? AMPK is a master energy sensor of the cells. It is very evolutionarily conserved kinase. So that is the main kinase which sense the level of energy in the cell. Like during the energy depletion, if the glucose level drops in the blood, or if there is a mitochondrial poison which damage the mitochondria and decrease the ATP production, AMP level or ADP level in the inside the cell is going to go up, and which directly binds to the gamma 70 of AMPK. AMPK is a heterotrimeric complex which has the catalytic alpha subunit and the scaffold beta or regulatory gamma subunit. During the energetic stress, either ADP or AMP will directly bind to gamma subunit and allosterically change the complex, which allows upstream kinase LKB1 or CAM kinase beta to phosphorylate AMPK on a activation site threonine 172, which activates the AMPK. When AMPK is activated, in other words, when cells are under energetic stress, AMPK is activated, and this kinase shuts down the anabolic pathways, which consumes a lot of energy, and turns on catabolic pathways to generate more energy to help cell survival. So next protein is mTOR. It stands for mechanistic target of rapamycin. It's a also very important evolutionarily conserved protein, threonine protein, which is the catalytic core of at least two multi-protein complex in the cell. Here we are talking about the mammalian cells, mTORC1 complex and mTORC2. I'm proud to say that these two very important protein complexes are discovered by my PhD supervisor, Dr. Sarbas, while he was a postdoc at MIT. These two complexes of mTOR share some proteins like Deptor, Gibel, and they have unique proteins like Raptor in mTORC1, Richter in mTORC2. mTORC1 is studied a lot more compared to mTORC2. mTORC1 sends a lot of diverse the environmental stimuli, growth factors, amino acids, energy, different types of stress, and regulates cell growth and proliferation. On the other hand, mTORC2 is relatively less studied, so only the mainly growth factor mediated regulation of TORC2 is well studied so far. There are a lot of questions what other inputs mTORC2 gets in order to regulate diverse cellular processes like actin cytoskeleton organization, cell proliferation, survival, etc. Both of these protein complexes of mTOR are important. For example, mTORC1 is when mTORC1 is active. For example, there is a inhibitor of mTORC1 called tuberous sclerosis complex. If in the patients either one of these genes are impaired, they're gonna experience cause cancer or cardiac hypertrophy, or insulin resistance, obesity, aging. It's very diverse. So like here we are talking about type 2 diabetes. And it was shown that inhibition of mTORC1 increased lifespan, so it is also involved in aging. And mTORC1 is also involved in fatty acid synthesis or fat storage processes. So it is very diverse function of mTORC1. And in terms of mTORC2, it is quite little known so far. It is shown to regulate glucose uptake because it stays downstream of growth factor signaling, insulin signaling. It also causes glucose intolerance, or it's also shown in different types of cancers, like PTEN. It's a oncoprotein, oncosuppressor, tumor suppressor. The deletion of PTEN causes prostate cancer, and if you inhibit mTORC2 in the PTEN null patients, it's gonna stop the cancer growth. So both mTORC1 and mTORC2 are very important complex. But the upstream of mTORC2 regulation is very less studied. So we are focusing on regulation of mTORC2 now. So I talked about AMPK and the mTOR complex. What is the relation of these two proteins? This axis, AMPK to mTOR, AMPK-induced inhibition of mTORC1 is well studied, but there is very little known about AMPK and the mTOR2 interactions. So I'm going to now focus on this axis. So AMPK and mTORC2 shown to have similar functions. As you can see here, like, both increase glucose uptake and suppress hepatic gluconeogenesis, and both increase support cell survival. So back in 2009, Finger Lab, before I was joining the lab, they did a tandem mass spec analysis for mTOR phosphorylation and found serum-1261 is highly phosphorylated in mTOR. Later, they conducted a kinome screen to identify the kinase for serum-1261 phosphorylation of mTOR, and surprisingly, they found out that all AMPK-related kinases are the ones responsible for serum-1261 phosphorylation, like AMPK alpha-1, alpha-2, or SIK2, and other marks. So in the past, serum-1261 phosphorylation was shown to promote TORC1 signaling. AMPK is a well-established suppressor of mTORC1. So there was a conundrum. Is AMPK gonna promote TORC1 signaling through phosphorylation of serum-1261 or suppress it? So at this point, we changed our direction to the other complex of mTOR complex 2. So before that, we confirmed that AMPK is the de facto kinase for serum-1261. We did a in vitro kinase assay where we isolated mTOR protein and incubated with active AMPK protein in vitro, and we tested the serum 1261 phosphorylation. As you can see here, both AMPK alpha 1 or alpha 2 of AMPK could phosphorylate serum 1261 within mTOR. This was in vitro. So we tested if AMPK phosphorylated mTOR in intact cells, and if it is phosphorylating both mTOR within TORC1 or within TORC2. So we activated AMPK with ICAR, a well-known AMP mimetic, which activates AMPK. Then we isolated mTORC1 or mTORC2 by immunoprecipitating either Raptor or Richter to see serum 1261 phosphorylation in these two complexes separately. So this is whole cell lysate. It's a combination of these two complexes. Yes, sure enough, ICAR increase serum 1261 phosphorylation in wild type cells, and not in AMPK double knockout, alpha 1, alpha 2 double knockout cells. So these are MAFs, mouse embryonic fibroblasts. These cells, AMPK alpha 1, alpha 2, DKO, double knockout, which lacks AMPK expression. This, then we also saw that serum 1261 is phosphorylated and it is increased with ICAR in within TORC1 complex, and within TORC2 in a AMPK dependent manner. So this data shows that AMPK is the kinase for mTOR serum 1261 phosphorylation. Okay. So we found that this is the kinase for TORC1, and it was shown that AMPK is an inhibitor of TORC1. What is happening between AMPK and TORC2? So first we asked if they interact each other. We precipitated Richter to pull down, isolate mTORC2, and as a result, AMPK is co-immunoprecipitated with mTORC2. You can see here. These are the control planes. So we confirmed that mTORC2 actually interacts with AMPK. And does AMPK affect mTORC2 activity? So we took wild type and AMPK double knockout maps and stimulated these cells with ICAR, AMPK mimetic, or we put them in glucose free medium to cause energetic stress. So in both cases, we saw a increased this AKT serine 473 is a readout for TORC2 activity. So when we look at TORC2 activity, we immunoblot for AKT serine 473 phosphorylation. So as you can see here, ICAR or glucose withdrawal nicely increased serum 126 AKT 473 phosphorylation in a AMPK dependent manner, which lacks in AMPK double knockout maps. It shows that AMPK increased TORC2 signaling to downstream effectors. So we try to confirm this result in vivo, in which we isolated mTORC2 complex by immunoprecipitating reactor. Yeah, the upper band is mTOR, and incubated with active AMPK complex in the presence or absence of AMPK inhibitor. As you can see here, in vitro active AMPK nicely phosphorylated mTOR and 71261 site, and which is blunted by treating with compound C, AMPK inhibitor. Then we washed off the AMPK from the complex and supplied the TURK2 substrate, AKT, to the tube, same tube. Then monitored the phosphorylation of AKT to see if the pre-incubation of mTORC2 with AMPK activates the AMPK catalytic activity. So as you can see here, incubating mTORC2 with active AMPK actually increased mTORC2 catalytic activity in a AMPK inhibitor compound C or mTOR inhibitor taurine sensitive manner. The insulin was taken as a positive control, rate of quantidation. So AMPK increased mTORC2 activity about 1.5-fold, which is quite comparable to insulin-induced TORC2 activation. So next question was, is this going to happen in primary cells? These cells we used in the previous experiments are the immortalized cells. And we have used some other different cell types from human or mouse. We have got the same result, and we have used different approach to decrease AMPK expression, like siRNA knockdown or shRNA knockdown. We have obtained similar result. So next we asked, is this AMPK mediated activation of TORC2 take place in primary cells? These are very fresh cells, just isolated from mice. To do that, to see the AMPK independence, we took AMPK alpha-1, alpha-2 fluxed mice and injected with Cree virus and excised AMPK alpha-1, alpha-2 specifically in the mouse liver, and the isolated hepatocytes, the liver cells, major liver cells from the mouse, and put in culture, then stimulated with metformin, which is a type 2 diabetes, the best or the most prescribed drug for type 2 diabetes, which activates AMPK. And as you can see here, stimulating primary hepatocytes with metformin nicely increased TORC2 signaling, which is very dependent on the state's AMPK. The AMPK knockout efficiency is here. So when in the primary hepatocytes which lacks AMPK, metformin failed to activate TORC2. That means the metformin-induced activation of AMPK is, mTORC2 is mediated by AMPK. And lastly, the most reliable or important experiment, of course, is in vivo. So we took the same mice, AMPK fluxed mice, and excised the AMPK alpha-1, alpha-2 in the liver by injecting adenocree virus. And after the excision of AMPK genes, we injected the mice with metformin. And after 1 hour, we harvested the liver and analyzed it. As you can see here, injecting metformin in wild-type mice nicely increased TORC2 signaling, and which is failed in the mice absent AMPK. All of these data shows that the energetic stress activates AMPK, and that activated AMPK increase TORC2 signaling. So in the beginning, I mentioned about the AMPK-mediated phosphorylation of mTOR serum-1261. Then we asked, is this phosphorylation required for AMPK to activate mTOR2? Then we generated a mice using the CRISPR-Cas9 technology. We mutated serum-1261 of mTOR to alanine and isolated the embryonic fibroblasts, and subjected those fibroblasts to AMPK activators like ICAR or metformin. All AMPK activators nicely increased TORC2 activity, but unfortunately, serum-1261 phosphorylation is not required for AMPK to activate TORC2. So we proceed to the function of these axes, saving the mice for later research. I will talk about later what we have found from these mice over time. So what is the function of AMPK-mediated activation of TORC2? In the beginning, I talked about cell survival during energetic stress. So we took wild type and AMPK deficient cells, MEFs, embryonic fibroblasts, and put them in a acute energetic stress, like AMP mimic ICAR for 5 hours, which cause energetic stress in the cell. So the cells which lacks AMPK showed a strong apoptosis or cell death. Apoptosis is cell death when we subjected them to energetic stress. Or if we take wild type MEFs and inhibit TORC2 and cause energetic stress, it also causes cell death. So how cells sense energetic stress is
excuse me, time schedule.
Oh, sorry. This is last slide. All right. So we also look under a microscope in live cells. So as you can see here, in the cells which lacks AMPK or mTORC2 activity, cause more cell death under energetic stress. I can skip this. And we have generated these serum-1261 alanine knock-in mice. Later we found that these AMPK-mediated phosphorylation of serum-1261 actually requires for amino acids to activate mTORC1, which is the the paradigm shift of our understanding the relation of AMPK and the mTORC1. So I thank my colleague here. This is our lab who participated in this research, and there's two people, Hugo and Brian, who initiated our project. And I thank all of our collaborators. With that, thanks for your attention, and I can take questions if we have time.
Since we are out of time, we have time only for one very short question. Okay. If no question, let's thank the speaker for his nice presentation. And please,
all right,
Dr. Barut, please introduce next speaker.
Hello, everybody. I'm glad to introduce the next invited speaker from England, Professor Dr. David Jenkins. He is working at the University of York in England. We have known each other for a long time, more than 20 years. We had very long collaboration with him. He is very well-known international nuclear physicist in the nuclear field. He finished his bachelor degree and the PhD degree at the University of York. Then he started as a postdoc in America, Argonne National Laboratory, then moved in to Liverpool University, his country. And since year 2002, he has been working at the University of York at the Department of Physics, where he is currently working as a professor of physics. His research area is in experimental nuclear physics that include nuclear structure, nuclear astrophysics, nuclear energy, homeland security, and medical imaging. Up to date, he has more than 130 publications in refereed journals with H factor of 28. And today he is going to deliver a talk as an invited speaker about radiation detector for industrial and medical application. We can start, Dave, please.
Yes, I'm going to do that now. Sorry, I had to quit to allow it to provide a presentation. Okay. Can you see my presentation now?
Yes.
You've got the PowerPoint. Is that working? Everybody can see?
It is black now.
It's black.
If you share your... Okay, it's now okay, yeah.
You see it, okay. Sorry, I haven't used this Teams before, so I'm just discovering how to use it. So thank you very much, Sefa, for the kind introduction, and I'm very happy to join your conference today. And with a change of topic from the last talk, I'm going to speak more about applicants, and I join you from York, where it's currently 9 o'clock in the morning. So our group historically has worked on experimental nuclear physics, and that means we've developed detectors which we take to international laboratories like CERN, which you've heard of, but many other laboratories around the world. And one of the interesting features of the detectors for nuclear physics is how relevant they are to many other areas of science, like particle physics, astronomy, even planetary science, but also more particularly, they solve problems in many areas of industry and medicine. And I've listed just a few there. Obviously, nuclear energy, border security, which is an area we talk about, nuclear decommissioning, how we clean up nuclear sites, medical imaging is a very important area, and so on. So let me show now some of the issues we have to deal with when we think about using detectors. And the main one is the different types of radiation and how those interact and how they lose energy in matter. Many of you, if you've done basic physics courses, will remember perhaps this sort of key description of the interaction of different types of radiation. How ours is often a very flat material. We often talk about a sheet of paper being sufficient to stop such particles. Beta particles, which are electrons or positrons, maybe need millimeters of material to stop in, whereas the other types of radiation we're interested in, gamma rays, the material to interact and stop in. So gamma rays can easily go through centimeters of matter, and neutrons can also go through centimeters of matter. What I'm going to speak about first is semi-conductive detectors, which are a very important class of detectors used in nuclear physics. I'll tell you an application of that in the beginning. So when we think about different types of materials, we have insulating materials where they're defined by having a very large energy gap between the valence band and the conduction band where the electrons are free to move. And then conductors like metals, where those two bands are fully overlapping and electrons are extremely mobile. But in between those, we have the very societally important area of semiconductors, materials like silicon and germanium, and also compound semiconductors, where there is a band gap of approximately 1 electron volt. And so when ionizing radiation interacts in those materials, it's easy to excite electrons from the valence band to the conduction band, leaving a hole in the valence band. And by applying an electric field, one can move those charge carriers away and produce an electrical signal in response to the ionizing radiation interacting with that semiconductor material. So let me now speak about a specific application of this, and this is a problem particularly in the UK where I live, but it's also one that's common to nuclear energy generation worldwide, and that is the cleanup of former nuclear sites. This has many, many different aspects, as you know. There's a huge range of plant and machinery and equipment there which must be removed, and the buildings themselves must be handled when they're returned to the pre-existing state. But one particular issue in these nuclear plants is pipe work. So here are some photographs of huge amounts of pipe work that you find in nuclear energy facilities, and particularly nuclear reprocessing facilities. And these pipes may have had radioactive material flowing through them in a liquid form. That material can be stuck on the walls of the pipe, and so when one wants to finish with that facility and clean it up, you need to deal with kilometers and kilometers of pipe. Now, of course, many of those radiations, as I showed, will come out of the pipe, and you can monitor from the outside and make a scan of the pipe to see if it's activated. But particular isotopes that only emit alpha particles are impossible to measure from the outside of the pipe because of the very short range of the material. So that would mean that you would have to cut up and section the pipe and examine it by hand in order to be sure that the pipe was clean of radiation and could then be recycled. If it was not, then you would have to deal with it in a particular way. So let's think about detector concepts that might solve that particular problem. So you could imagine having a detector which you put in the middle of this pipe, but that is not particularly suitable because the alpha particles already lose energy just passing through centimeters of air. So they would have lost a lot of energy already before they actually reach your detector. The alternative is you could have maybe many individual detectors in a ring around the walls of the pipe and try and detect the alpha particles in that way. And that could be quite complicated and quite expensive. If you think about it, the most elegant solution would be to have a cylindrical detector because you have a cylindrical pipe. So a cylindrical detector could go round a little bit away from the walls of the pipe so that it would be highly efficient all the way round. And of course, the efficiency at all points of the detector would be the same because the distance would always be the same from the walls of the pipe. You could get more complicated by having, will this not, is this not display, Stefan?
No, because you haven't started animation yet. Now it could be, yeah.
Let me just try one different thing to share it in a different way, because I think if I share my screen, I think maybe it's going to be better.
More efficient.
I think I'm sharing the wrong thing, and now I can't find the PowerPoint. Sorry. I apologize. This is a new thing for me. I think I was doing it the wrong way. This is better. Okay, so we could also think of such a detector that you could change the geometry, so you can send it down different pipes with different diameters as it changes. So this technology, semiconductor is very heavily used in nuclear and particle physics, and here are many examples of barrels of silicon detectors used in physics applications. But none of these are actually really cylindrical. They're making cylindrical barrels, but they're using silicon detectors. So this is a good technology. We know about it. It's well developed, and it's relatively cheap. But what we realized within our group and our collaborators in a photonics group at York is that when you have they're highly flexible, and as you can see in this video, you can actually bend it into a cylindrical geometry. Of course, if you bend it too much, then it will actually finally break, as you'll see here. But as long as you don't bend it too far, it will keep that particular geometry, and you can have a cylindrical detector. This is our initial concept for what such a detector would look like. So it's a probe that the pipe, and it has a sensor around the middle, this cylindrical sensor that can measure the alpha particles on the internal walls of the pipe. And then we went ahead to try and make such detectors. So in these videos, you see some of the work being done in the clean rooms at York to transform a silicon wafer, so a high quality, high resistance silicon wafer, which we need to turn into a diode by doping it with suitable elements like boron on phosphorus. There's many different stages in cleaning and preparation, doping, and placing these things into a furnace to transform that material into a radiation detector that has a junction in it. And this is described in this paper here. And I should mention this work was also in collaboration with Chromec, a company who make radiation detectors. So this is what the prototype detector looks like, the bare detector, and you can see it being bent around the frame into that nice curved geometry to be suitable for the pipe. Most of the pipes that we're interested in, by the way, are 2-inch diameter, or i.e. a little over 50 millimeter diameter pipes. Obviously, this sort of thing is too fragile and delicate to put directly into the pipe, so we make an instrument, a probe, which has these detectors behind these slots on the instrument, so that it's protected and it's not in direct contact with the walls of the pipe where it would get damaged or potentially contaminated itself. This video shows some testing of this prototype system. We have an alpha source, so there is an alpha particle source mounted on the outside of this plastic pipe. And you can see on this oscilloscope that when the detectors are moved away, you see no signal. When you move the detector in the passage of the source, you see pulses on here, which are alpha particles being detected by this curved detector. The next question is, how sensitive does this detector have to be in order to satisfy the requirements of the application? So we want to show that this pipe is clear of activity, and we carry out a Monte Carlo simulation using a software package called Geant4, developed by CERN. So we have a randomly occurring contamination on the walls of the pipe, and these are the alpha particles coming out. Here is a model of the detector, and this simulation shows that if you want to show that the minimum level of activity is 0.4 becquerels per centimeter squared, then you can examine this at the rate of 3.5 minutes per. Whoop, something's changed. I think I've hit the wrong. What's going on? Oops. It takes 3.5 minutes per 1 meter of pipe to scan this pipe. And I'll show now a video of this thing working. So this is a demonstration of it moving down a pipe on a test site, and it's designed to move slowly down on a tether. So this is a field trial. Whoa. Okay, and you get an impression how that's working. So now let me show something about a different type of detector, which is scintillator detectors, and something about how these can be used in industrial applications. Oh, I think I made a mistake, and I've given control to somebody else who's also controlling the slides. I wonder if okay, that's stopped now, good. I think somebody else was moving the slides on. I think this was a feature of this software I didn't realize. Okay, so something about scintillator detectors. There are two main types of scintillator materials that we find. There are inorganic scintillator crystals. So some of these crystals, like sodium iodide, cesium iodide, and so on, these are materials where when a ionizing radiation interacts with it, it excites electrons in the material, and when these electrons drop back down in energy, then light is emitted, scintillation light, which can be in the visible or the ultraviolet wavelengths. And this sodium iodide detector technology goes back even to the 1940s and 50s, extremely common and well understood detector material used very extensively in industry, particularly for measuring gamma rays. We also have organic scintillator materials, and I'm showing one example here, which is plastic scintillator materials. So plastic is also a scintillator. Here the scintillation is driven by the molecular characteristics of the material. So ionizing radiation excites higher lying in the material. The emission of light from those is not very efficient, and so what people do is normally add a dye and wavelength shifters to that material to make it a more efficient emitter of scintillation light, and also often to shift the wavelengths into regions that are more suitable for photo detectors that collect that scintillation light. In terms of the detectors which exist for the scintillation light, the traditional and most commonly found one is the photomultiplier tube that probably most people might be familiar with. So at the front of that, it has a photocathode. The scintillation photons hit that cathode and produce electrons. these electrons are steered through this instrument and find accelerating voltages that multiply the number of electrons and accelerate them, and that current is collected at the end of the tube. But these detectors are physically quite large, so here's a typical photomultiplier tube. It's also inherently fragile because it's an evacuated tube with a glass window, and it needs to operate at high voltage. About 10 years ago, replacement technology came along for this that's driven by advances in medical imaging, and this is the silicon photomultiplier, and an example is shown here at the bottom. So these are very small devices, maybe a few millimeters square, smaller than a postage stamp. And on those, they have tens or hundreds of thousands of tiny pixels, which are avalanche photodiodes. And the idea is when an individual photon falls on one of these photodiodes, it produces a small pulse. So you have, if you have more pixels than you have photons, you have a signal that's proportional to the number of photons. And this silicon photomultiplier that can run at low voltage, maybe 30 volts, even run from a battery, has completely changed the way we can do scintillation detectors and what's possible with that sort of application. So I'm going to show a couple of simple examples where this has been applied in different areas of societally relevant technology. So one is a miniaturized positron detector for PET isotope assay. So positron emission tomography is a very important medical imaging technique, particularly used for cancer diagnosis, for example. And the idea is that one puts a radio tracer in the body, specifically a positron emitting radio tracer. And when these positrons are emitted from that particular isotope, they travel a very short distance in the body, maybe about a millimeter, and then they annihilate with an electron and produce two gamma rays emitted in a near back-to-back geometry. You detect these back-to-back emitted gamma rays, and you use that, and I'm not going to go into all the details here, but you use those lines of response, as they're called, to reconstruct a functional image inside the body and see, for example, diseased organs. But one of the key things is we need to understand when people produce these isotopes and they produce particular medical compounds in solution, they want to know how much activity is in those. Are they clean? Is it only one radioisotope involved in there? And there's all sorts of careful assay that needs to be done of those isotopes before they are used. Now, traditionally, the way that you would count the level of activity in those sort of medical isotopes is in the following system. And these are quite physically large detectors. What they're trying to detect is the gamma rays emitted from that radioisotope, and it's done with a large gamma ray detector, a sodium iodide detector, in this large lead-lined pot. So this is quite a substantial and heavy benchtop system that you would use for making these measurements. Now, a lot of the interest in PET isotopes and the production of them is whether one can miniaturize all this equipment and actually have what they call a lab on a chip. So have a small microfluidic chip with very small channels in a sort of acrylic plastic type material where you manipulate these isotopes, and you might want to do other sampling on them. And we had the challenge to develop a detector which would be able to measure the level of activity in those isotopes, but not use such a big, bulky equipment. So I had a PhD student, Nuray Yavuz-Kanat, who worked with me at York and is now actually working in Bitlis Eren University in Turkey, and she's still collaborating with myself and with Sefa on future projects. And she developed for us a very nice system where we'd have a very small channel in a microfluidic chip, and the isotope passes directly through a channel in a plastic scintillator material. And here we don't detect the gamma rays that are coming from this isotope, we detect rather the positrons. So these positrons have an intrinsically short range of about 1 millimeter. They go into the plastic scintillator, they produce light, and this light is detected on the bottom by the silicon photomultiplier device. And what you can see here on the bottom left is that this device can also detect the activity. So these are plugs of radioisotope being passed through this channel every few minutes, and you can see that as they go through, you measure a signal. The red one is the conventional benchtop detector, and the blue one is this tiny microfluidic system. And you can see that the two are measuring the same thing, and we have a joint patent on this technology and are trying currently to develop this so it could be used more widely in this area of medicine and preparation of medical isotopes. I'm going to briefly show one more example. So I've talked about alpha particles, I've talked about a type of beta particles in the last example, positrons. I'm going to finish by talking about gamma rays. So gamma rays are probably the most important radiation detection application. They're the ones that are most used in industry and in medicine. And I'm going to tell you about development of a handheld gamma ray detector for homeland security. So what we did here, we worked with this company, Chromec, that I mentioned earlier. This is a company based about 100 kilometers north of where we are in the north of England. And what they wanted to do was develop a handheld detector that you could take around for purposes of border and homeland security. So one of the particular concerns in security is whether people could steal radioactive materials, transport these illegally, and there's a particular concern that people might try and blow up this material in what's called a dirty bomb. So you could contaminate a city, cause a lot of panic and so on. No one has actually done that as yet, but there's a lot of concern that if people had access to materials, they could move them around. How do you detect those materials in a city or a port or so on? And you obviously need detectors which are convenient, can be held in the hand or even worn by people as they're doing their regular duties. And that's what these silicon photomultipliers offer, because they're extremely small and compact relative to the photomultiplier tube. So if we couple those to scintillator materials like cesium iodide, these inorganic crystals, we can make a small handheld detector. And this is the original device that we made for Chromec. That was a handheld instrument where it detects the radiation, the gamma radiation, and more particularly it identifies what is the isotope which is emitting those gamma rays. So it gives you the nature of the threat as well as telling you about the level of radiation. And Chromec packaged this into a suite of wearable instruments called the D3S, and the black unit is the detector, and that can couple to a mobile phone to visualize the data that's coming from this device. It can also be put into a large network and send back information to a base. And you can see that this is really a thing the size of, this is real scale, so the detector thing is smaller than a phone. It can be worn by police, firemen, and so on when they're investigating an incident, or they can carry it in their regular work, so it's continuously building up information. This is significantly more compact and more robust than this old-fashioned detector technology with a photomultiplier tube. This would require high voltage and a large amount of instrumentation. It wouldn't be practical to carry such a device around. This modern replacement allows you to have a much more flexible instrument. And this has been deployed a lot, particularly in the US. The American government bought 10,000 units of this detector. It's also being used at other places around the world and across Europe. It can all be networked, so as people are walking around, as shown on this map, imagine that there are different people carrying these instruments. They're building up information, and you can triangulate this information to try and work out where is the source of that radiation, where has somebody secreted some radioactive isotopes that they shouldn't have, that they're hidden in a building or something like that. Okay, so thank you for bearing with me and some of the issues I've had in learning how to use the Teams. So radiation detectors that we use in our regular work in experimental nuclear physics are also relevant to many applications in industry and medicine. There's continuous improvements in this technology and lots of innovation coming along. As I've shown you, there's a lot of interest in taking existing technology and miniaturizing it, so making it much smaller, making it much more portable. I've also shown you an example of making flexible detectors that have an elegant geometry, like a cylindrical geometry, so they can go inside a pipe or investigate the interior of different objects. And I would also say that there is clearly a lot of advantage in collaborating between academia, universities and research labs and industry. I've shown you these examples how we could work on the basic detector technology, but the industrial collaborators were the people able to make that into a real product and a rugged, robust product that could be used in the real world, and that's been very significant for our research. So with that, thank you very much again for the invitation, and I will finish there. Thank you.
Thank you, Dave, for your valuable talk and the different information from the different aspects, starting from the security and the health issues. Is there any question to Dave? Hello?
Someone's coming.
Two people appeared. Do you have question, Professor Ratbarut, or from the Kazakh side? Nothing is coming, probably. Okay. So thank you. We really thank you to give this talk, and we are very pleased we are honored to have you during this conference as an invited speaker. Thank you very much once again. If not, I will close this session, and I'll hand to Mr. Toga. Yeah, please.
Yeah. Thank you, Professor David Jenkins, and for attending our Congress, and we are honored to host you. We hope you next time also we will be see you at our Congress. Thank you.
Thank you.
So now we are, yeah, Professor Tolga, I think we come to end this session, and thank you to attending this session and making contribution to our session.
Okay, now today our program is finished.
Yeah, is over. Yeah, for today is over.
All the speakers, and almost finished on time. Only
yes.
10 minutes delay, but 10 minutes because of technical reasons, not because of the.
Thank you very much to rector of the university. We very appreciate that you participate in this congress. Thank you very much for all of these participators to join us and to support us. I think it's the next time will be offline meetings. I hopefully this is a hard time we survive very well.
Yeah, we
It's
hope
very
so.
glad to meet Mashinka, you. I think with the next our celebrating anniversary, you visited us to. Was from Rector Erlan Batashevich very request to invite you this our celebration events.
Oh,
Thank you very much, all of them.
Thank you too. Then see you tomorrow. And
Tomorrow at noon in Kazakhstan time and at 9 a.m. on Turkish time, yes?
Yes, that's correct. Yeah, that's correct.